connecting two oceans through one of the most hostile jungles on Earth. A skyscraper that came to define the world's most iconic skyline. A sea defense system that saved a country. And 6 more megaprojects that pushed the limits of engineering and became wonders of the world. Built across more than a century, these creations permanently changed the landscapes, economies, and lives of everyone around them. The American Society of Civil Engineers in 1994 and the BBC in 2003 designated these structures as the greatest engineering wonders of the modern world. In 1930, with America in economic freefall, unemployment climbing past 25%, and businesses collapsing by the thousands. However, at the same time, 3 skyscrapers were locked in the race to become the tallest building in the world. The 40 Wall Street, initially known as Manhattan Company Building, and Chrysler Building were being constructed simultaneously, only kilometers apart from each other. Former business partners turned rivals. Harold Craig Severance and William Van Allen were the main architects on the 2 projects. Harold Craig was building 40 Wall Street that was planned to become the next head office for the Manhattan Company and the tallest building in the world. Meanwhile, William Van Allen was working with Walter Chrysler, America's automobile giant, who wanted to build something even bigger. He wanted a tower that would rise higher than any other structure ever seen. Locked in a competition, the Manhattan Company building reached a final height of 281 meters. But that record was soon broken, as the Chrysler building added a 38-meter spire at the top to reach 319 meters. However, just a few blocks away, former General Motors executive John Jacob Raskob was planning something even bigger. It was the Empire State Building. Born through a rivalry between businessmen, it would go on to become a global icon over the next century. The site on 34th Street was cleared by demolishing the original Waldorf Astoria Hotel, one of the grandest buildings in New York. Demolition finished in late 1929. The stock market crashed weeks later. Construction began in March 1930 anyway. What followed was, by any honest measure, one of the most extraordinary construction feats ever attempted. The original design for the Empire State Building had 50 floors. However, Raskob wasn't willing to accept second or third place and kept on adding more floors. During construction, the design was changed 15 times to finally incorporate more than 100 floors. Despite the race to build taller, the constant design changes, and the economic downturn, the construction timeline was very ambitious. The target was 410 days from groundbreaking to completion. At the time, serious engineers considered that timeline a fantasy. A building of that scale typically took years. For comparison, the Chrysler Building was completed over 7 years. The Empire State Building's developers went on to smash all conventional engineering wisdom. They engineered the entire supply chain around speed. Steel was fabricated in Pittsburgh and shipped to Manhattan on a schedule so precise that each shipment arrived floor by floor, just as the workers above needed it. Nothing sat in storage. There was no room for it. At peak construction, 3,400 men worked the site simultaneously across multiple floors, going up at the same time. The building rose at more than 4 floors per week. 5 workers died during construction, a number far lower than anyone familiar with the conditions would have predicted. They finished 12 days ahead of schedule. The total cost came to just under $41 million in the Depression-era economy. In today's terms, it's roughly $700 million. What makes that figure remarkable is that the original budget was higher. The economic collapse actually drove down the cost of labor and materials so sharply that the project came in under its own estimates, even while going faster than planned. The Empire State Building opened on May 1, 1931. President Hoover switched on the lights by telegraph from Washington. The world took notice as the Empire State Building reached a height of 381 meters to the roof. An antenna spire was added to the top of the building, taking its height to 443 meters. But as iconic as the Empire State Building was, it felt like a disaster early on as almost nobody moved in. The Depression had gutted Manhattan's commercial real estate market completely. Offices sat empty across the city, and the Empire State Building, designed to house tens of thousands of workers, was chronically, embarrassingly vacant. New Yorkers nicknamed it the Empty State Building. For years, observation deck ticket sales were the primary thing keeping the finances afloat. The building didn't turn an actual profit until 1950, nearly 2 decades after opening. There was also the mooring mast. Roscoe had added it to the roof partly to guarantee the height record, and partly because he genuinely believed transatlantic airships would dock there, allowing passengers to descend directly into Midtown Manhattan. The physics of mooring a massive hydrogen airship above one of the windiest urban environments on the planet proved catastrophic in practice. It was used for one semi-controlled public docking and quietly converted into a broadcast antenna shortly after, which turned out to be considerably more useful. The building held the world height record for 41 years. Nothing touched it until 1972, when the North Tower of the World Trade Center surpassed it. Since then, roughly 20 buildings worldwide have exceeded it, including the Burj Khalifa in Dubai, which stands more than twice as tall. In the relentless arithmetic of skyscraper records, the Empire State Building has long since been left behind, and yet it remains the most recognizable building on Earth. That's not sentiment. It shows up in studies, in surveys, in the simple fact that its silhouette is understood globally by people who couldn't point to New York on a map. As soon as it was commissioned, the Empire State Building became a pop culture icon and has remained that way ever since. King Kong climbed it in 1933, 2 years after it opened, and that image burned itself into popular culture permanently. Cary Grant waited at the top in a film that turned the observation deck into shorthand for romantic longing. It has appeared in more movies than any other building in history, not as a backdrop, but as a character, a fixed point, the thing the camera finds when it wants to say, "This is New York." In 1994, the American Society of Civil Engineers named it one of the 7 wonders of the modern world, recognition not just of its height, but of the construction achievement behind it, the speed, the precision, the sheer organizational complexity of raising 102 floors in 410 days with 1930s technology. That's what earned it the designation, not what it looks like, what it took to build it. Around 4 million people visit each year. The steel frame is unchanged from 1931. On a clear day, you can see it from 50 miles out. What it is, underneath all of that, is a building that had no business succeeding. Built at the worst possible economic moment, by men motivated by ego rather than demand, into a market that ignored it for 2 decades. It survived all of that and has become synonymous with New York ever since. Just like another tower in North America, that has come to define an iconic skyline. For most of the 20th century, Toronto had a problem that became a regular hindrance over the years. The city was growing fast. New skyscrapers were going up across downtown through the 1960s and early 70s, and every one of them was doing the same thing, interfering with television and radio signals across the region. The taller the buildings got, the worse the interference became. Broadcasters were losing signal, communications were degrading. The city's own growth was strangling its ability to communicate. The solution, proposed by the Canadian National Railway in 1972, was to build a single transmission tower so tall it would clear every rooftop in the city by a margin that no future development could threaten. A tower that would solve the problem permanently. What they ended up building held the title of world's tallest freestanding structure for 32 years. The engineering brief was straightforward in theory and brutal in practice. The tower needed to be tall enough, at minimum 300 meters, to broadcast above the existing skyline with room to spare. It needed to be structurally stable in a city that sits in a seismic zone and faces serious wind loads off Lake Ontario. And it needed to be built on a site with difficult soil conditions, right at the edge of the lake, where the ground offers considerably less cooperation than an engineer would like. Construction began in February 1973. Workers poured a massive hexagonal concrete base and sank it deep enough to anchor the structure against the lateral forces a tower of this height would face. The concrete shaft above it, hollow, hexagonal in cross-section, reinforced with thousands of tons of steel, was poured continuously using a technique called slip forming. A circular platform slowly climbed the structure as the concrete was poured, allowing crews to work around the clock without stopping. Any interruption risked a structural weakness in the concrete, which in a tower of this scale was simply disastrous, which slowed down construction to a speed of roughly 1 meter per day. At 447 meters, the main shaft was complete. Above that, workers installed a steel antenna mast, which pushed the total height to 553 meters, or 1,815 feet. Getting that mast into position required a Sikorsky S-64 sky crane helicopter, which made 45 lifts over the course of 3.5 weeks. Each lift had to be precise. At that altitude, wind conditions were unpredictable enough that crews had to abort and reschedule repeatedly. The work was slow, exposed, and offered no margin for error. The whole project took 40 months and cost 63 million Canadian dollars, roughly 350 million in today's terms. It opened in 1976 and immediately became the tallest freestanding structure on Earth, surpassing the Ostankino Tower in Moscow, which had held the record since 1967. Toronto, a city not typically associated with superlatives, suddenly had the most dramatic piece of infrastructure on the planet rising out of its downtown waterfront. The practical function worked exactly as intended. A single centralized transmission point eliminated the signal interference problem across the region. Broadcasters moved their antennas to the tower, and the issue was solved. In terms of pure engineering utility, the CN Tower did precisely what it was designed to do, but what it became in the years after opening was something the Canadian National Railways Planning Department almost certainly didn't model in their original projections. The observation deck drew visitors immediately and kept drawing them. The glass floor, installed in 1994, 342 meters above the ground, became one of the most photographed spots in Canada. The Edgewalk, introduced in 2011, allowed visitors to walk hands-free along the outside of the main pod at 356 meters, attached to an overhead rail by nothing more than a harness and whatever composure they could maintain. Roughly 2 million people visit the tower every year. A significant portion of them choose to stand on glass above a 300-meter drop and stare down. The revolving restaurant at the top completes one full rotation every 72 minutes. On a clear day, the view extends to Niagara Falls and across the lake into New York State. The height record fell in 2007 when the Burj Khalifa's construction in Dubai passed 553 meters on its way to 828. The CN Tower no longer holds the record it was never actually built to hold. It still holds the skyline. Toronto's downtown has continued to grow around it for 50 years. Dozens of towers have gone up in its shadow. The city has become one of the fastest-growing urban centers in North America, with a skyline that changes visibly year on year. And through all of it, the CN Tower remains the fixed point. The thing every aerial shot finds first, the structure that tells you where you are before anything else does. It was built to fix a broadcasting problem. It cost $63 million and took just over 3 years. The problem it was built to solve was fixed immediately and has never returned. Everything else the tower became was unplanned. Next on the list is yet another tall structure that has become the reference point for a city. In 1919, an engineer named Joseph Strauss submitted a proposal to build a bridge across the Golden Gate Strait in San Francisco. The design was, by most assessments, hideous, a clunky hybrid cantilever structure that looked like it belonged over a railway yard rather than one of the most dramatic natural harbors in the world. The city wasn't interested. Strauss spent the next decade lobbying anyway. By the time construction was approved in 1930, the design had been completely overhauled by his chief engineer, Charles Ellis, and architect Irving Morrow, the men who actually gave the bridge its final form. Strauss took the credit. Ellis, who spent months doing the complex mathematical calculations that made the bridge structurally possible, was fired before construction began and received no official recognition for his work for decades. That tension between vision and credit, between ambition and reality, runs through the entire story of the Golden Gate Bridge. The engineering problem was genuinely formidable. The Golden Gate Strait is not a cooperative place to build anything. The channel is over 1,500 meters wide at the crossing point, with currents running at up to 7.5 kilometers per hour. The water is 67 meters deep at the South Tower location. Fog rolls in from the Pacific with enough regularity that visibility drops to near zero for significant parts of the year. The whole region sits in one of the most seismically active zones in North America. And at the time construction was proposed, the longest suspension bridge span in the world was roughly half the distance that the Golden Gate required. Nobody had built anything like it before because nobody had needed to. The strait had functioned as a natural barrier between San Francisco and Marin County for the entire history of European settlement, with ferry services handling the crossing. As the region grew through the early 20th century, the ferries became increasingly inadequate. A bridge was the obvious answer. The engineering required to build one at this particular location was the problem. Construction began in January 1933. The South Tower Foundation, planted directly on the floor of the strait 300 meters from shore, required workers to operate underwater in open ocean conditions with strong currents and poor visibility. A protective fender, a concrete barrier around the base, had to be constructed first, the water pumped out, and then the foundation work completed inside it. It was slow, dangerous, and repeatedly disrupted by the sea refusing to behave predictably. The towers rose 227 meters above the water, stringing the main cables between them, each cable made up of 27,572 individual steel wires, spun in place over months, required techniques that pushed the limits of what the industry knew how to do. Each finished cable was 92 centimeters in diameter and capable of bearing a load that would have seemed fictional to bridge engineers a generation earlier. Strauss was obsessive about worker safety in a way that was genuinely unusual for large construction projects of the era. He mandated hard hats on site at a time when most construction workers considered them unnecessary. He insisted on safety nets strung beneath the roadway during construction, a significant expense that many considered unjustifiable. Those nets saved the lives of 19 men who fell during construction and survived. They became known as the Halfway to Hell Club. 11 men died on the project, 10 of them in a single accident in February 1937, when a scaffold fell through the safety net and took workers with it into the strait below. One man died in a separate incident earlier in the project. The bridge opened on May 27, 1937. 200,000 people walked across it on the first day before vehicles were allowed on. The roadway deflected noticeably under the weight of the crowd, a detail that unsettled onlookers, but was well within the bridge's design tolerances. What happened in the years after opening built the bridge's mythology layer by layer. The color, officially called International Orange, was chosen by Irving Morrow partly for aesthetic reasons and partly because it made the bridge visible in the fog that regularly obscures the strait. The U.S. Navy had lobbied for it to be painted in yellow and black stripes as a visibility aid for shipping. The fact that the bridge is the color it is comes down to an architect overruling the military on aesthetic grounds. In 1987, on the bridge's 50th anniversary, the same idea from opening day was repeated: pedestrian access before vehicles. Around 300,000 people showed up. The wait was so much greater than the 1937 crowd that the bridge's roadway flattened out completely, losing its characteristic upward curve. Engineers had accounted for load but hadn't modeled this particular distribution of it. The bridge held, but it was a closer calculation than anyone had anticipated. Alfred Hitchcock filmed Vertigo on and around the bridge in 1958. It has appeared in more films than almost any other structure in the world. When the fictional version of San Francisco is destroyed in movies, the Golden Gate Bridge goes first, a cinematic shorthand so established it has become a cliché that filmmakers still can't resist. The bridge was named one of the 7 wonders of the modern world by the American Society of Civil Engineers in 1994, recognized specifically for the audacity of its span, the difficulty of its construction environment, and the elegance of a structure that managed to be both a feat of engineering and one of the most beautiful man-made objects in the world. It carries roughly 10 million vehicles a year, It has been repainted continuously since the day it opened, the maintenance crew finishing one end and starting again from the other in a cycle that never stops. The bridge moves. On a hot day, the roadway can expand by over a meter. In high winds, the deck can sway several feet laterally. It was designed to do exactly that. Joseph Strauss died in 1938, a year after the bridge opened. Charles Ellis, the engineer whose calculations made it all possible, lived until 1949 and spent those years largely uncredited. The bridge still has his math holding it up. We now move across the Atlantic to another mega project that saved a country from catastrophic tides. On the night of January 31st, 1953, a combination of a high spring tide and a severe northwestern storm pushed a wall of water into the southwestern Netherlands that the existing defenses simply couldn't handle. Dikes broke in dozens of places simultaneously. Seawater poured into low-lying polders in the dark, while most people were asleep. By morning, 1,836 people were dead. Nearly 100,000 were homeless. Almost 200,000 hectares of agricultural land were submerged in salt water. Entire villages had ceased to exist overnight. The Netherlands had flooded before. The country had been fighting the sea for centuries. Roughly a third of its land sites below sea level, and another third sits barely above it. But 1953 was different. The scale of it, the speed of it, the fact that it happened in a modern European country with existing flood infrastructure. It made the political case for something that engineers had been proposing for years and governments had been deferring. 3 months after the flood, the Dutch government commissioned the Delta Works. The plan was sweeping in a way that's difficult to convey without listing what it actually involved. Over the following decades, the Netherlands constructed 13 major dams, sluices, locks, dikes, and storm surge barriers across the river delta in the southwest of the country. The objective was to shorten the Dutch coastline by 700 kilometers, eliminating the most vulnerable stretches of open water that had allowed the 1953 storm to do what it did. The engineering challenges varied dramatically from structure to structure, which is part of what makes the Delta Works remarkable as a collective achievement. Some sections required straightforward dike reinforcement. Others required closing open sea channels several kilometers wide in water depths that made conventional construction methods unworkable. The Oosterscheldekering, the Eastern Scheldt storm surge barrier, became the centerpiece and the hardest problem. Engineers had originally planned a closed dam across the estuary, which would have been simpler to build. Environmental opposition in the 1970s forced a redesign. What replaced the original plan was a structure of considerably greater complexity, a semi-permeable barrier with 62 massive concrete piers supporting steel gates that sit open under normal conditions, allowing tidal flow and preserving the estuary's ecosystem and close automatically when storm surges threaten. The piers alone weighed up to 18,000 tons each. Moving them into position required purpose-built vessels that didn't exist before the project. The Dutch had to design and construct the ships needed to build the barrier before they could build the barrier itself. The gates, each one the size of a house, were engineered to withstand the full force of a North Sea storm, while operating reliably after sitting open in saltwater for years between closures. It took 10 years to build and cost the equivalent of several $1 billion in today's terms. It is, by most engineering assessments, the most technically complex flood defense structure ever constructed. The Maeslandkering, completed in 1997 as one of the final components of the Delta Works, protects Rotterdam, one of the largest ports in the world. It consists of 2 enormous hollow steel arms, each the length of the Eiffel Tower laid on its side, hinged on either bank of the waterway. Under normal conditions, they sit open in dry docks on each bank, completely invisible to shipping. When a storm surge is forecast, they swing out, meet in the middle of the channel, and seal it. The entire operation is automated, triggered by a computer system with no human intervention required once the decision to close is made. They have closed in earnest a handful of times since 1997. Each time, a structure roughly the size of 2 Eiffel Towers has silently swung shut across one of the busiest shipping lanes in Europe, held back the sea, and then reopened. Since the Delta Works were completed, the Netherlands has not experienced a major flood disaster. The 1953 flood killed 1,836 people. The infrastructure built in response has protected millions. What makes this wonder different from every other on the list is that most people will never see it. There is no observation deck. There is no famous silhouette. The Eastern Scheldt Barrier is impressive if you know what you're looking at, but it doesn't photograph like a bridge or a tower. It sits in the water and does its job. In a country where the alternative is the sea reclaiming the land entire generations built their lives on, doing its job is enough. In 1962, Brazil and Paraguay shared a border, a river, and almost nothing else in common. Brazil was the largest country in South America, resource-rich and growing fast. Paraguay was one of the smallest, landlocked, and poor in ways that went beyond economics. The idea that these two countries would agree on anything ambitious was optimistic. Then someone looked seriously at the Paraná River. The Paraná is one of the great rivers of South America, 4,880 kilometers long, draining a basin larger than Western Europe. Where it runs along the border between Brazil and Paraguay, it drops in elevation in a way that had been catching engineers' attention for decades. The hydroelectric potential at the right location on that stretch of river was, by any calculation, enormous. The question was whether the two countries could agree on how to develop it. In 1973, after years of negotiation, they signed the Itaipu Treaty. Construction began the following year. What came next was one of the largest construction projects in recorded history. Before a single concrete pour could begin, the engineers faced a problem that had no straightforward solution. The Paraná River was still flowing. At the Itaipu site, it moved 8,500 cubic meters of water per second on average, surging far higher during seasonal floods. Building a dam across an active river of that volume meant the river had to go somewhere else first. The solution was to dig a bypass channel, 2 kilometers long, 150 meters wide, 90 meters deep, cutting through solid rock beside the construction site. Moving that volume of rock required 50 million tons of earth and stone to be excavated. The bypass channel alone, before a single dam structure was started, was an engineering project larger than most things built at the time. Then they diverted the river into it and built the dam in the dry. The main dam structure stretches 7.9 kilometers across the river. The powerhouse contains 20 generating units, turbines so large that each one individually could power a mid-sized city. The reservoir behind it holds 29 billion cubic meters of water, flooding an area of 1,350 square kilometers. An artificial lake that drowned several towns, displaced around 40,000 people, and submerged a set of waterfalls called the Guaíra Falls, which had been among the most spectacular in the world. The Guaíra Falls are gone. They exist now only in photographs. Construction ran from 1975 to 1984. At peak activity, 40,000 workers were on site. Over the life of the project, roughly 150 workers died. The total cost reached approximately $19 billion, making it, at the time of completion, one of the most expensive construction projects ever undertaken. What it produced was a generating capacity that was, for a period, without parallel anywhere on Earth. Itaipu's 20 turbines can produce 14,000 megawatts of power. In 2016, it set a world record by generating 103.1 terawatt-hours of electricity in a single year, more annual electricity production than any power plant in history at that point. For decades, it supplied roughly 80% of Paraguay's entire electricity needs and around 17% of Brazil's. A single dam on a shared border powering most of one country and a significant fraction of another simultaneously. The economics of the arrangement have never been entirely comfortable. Under the original treaty terms, Paraguay, which uses a fraction of the power Itaipu generates, sells its surplus share back to Brazil at a fixed price set in 1973. For decades, Paraguay argued those terms were exploitative, locking a small, poor country into a contract that paid them far below market value for energy produced on their own territory. Renegotiations have happened. The tension has not fully resolved. Being named one of the 7 wonders of the modern world, is a recognition that the scale of the engineering, the diversion of one of the world's major rivers, the construction of a 7.9-kilometer dam, the installation of a power generation system of that capacity represented something genuinely without precedent at the time it was built. The Chinese Three Gorges Dam, completed in 2003, eventually surpassed Itaipu in both installed capacity and annual generation. Itaipu no longer holds the records it once did. What it still holds is the river. The Paraná runs through the turbines today, as it did the day they switched them on. The bypass channel cut through solid rock in the 1970s still sits beside the dam, empty now, a ghost of the engineering problem it was built to solve. The towns beneath the reservoir are still down there, somewhere under 29 billion cubic meters of water. And the Guaira Falls, which once thundered loud enough to be heard from miles away, are silent. Next up, we have a megaproject that was planned over a century and finally breached the waves to connect Europe. The idea of a tunnel under the English Channel is older than most people assume. A French engineer named Albert Mathieu proposed one in 1802, a horse-drawn carriage tunnel lit by oil lamps, with an artificial island in the middle of the channel for ventilating the thing. Napoleon expressed interest. The British, characteristically, did not. Over the following 180 years, the tunnel was proposed, studied, started, and abandoned more times than anyone involved would have liked to count. Work actually began twice, once in 1880 and again in 1974, before being stopped on both occasions by British political opposition rooted in a single, consistent anxiety that a fixed link to continental Europe represented a threat to the island's security that no amount of engineering benefit could justify. It took until 1988 for construction to finally begin in earnest. By then, the original concept had been refined, revised, and debated for the better part of 2 centuries. The geology under the channel turned out to be one of the few cooperative elements of the entire project. A layer of chalk marl, dense, relatively impermeable, consistent in depth, ran beneath the seabed at a workable depth for most of the crossing. It was almost as if the ground had been designed for tunneling, which made the work faster and more predictable than comparable projects in more difficult rock. There were 3 tunnels to bore, 2 rail tunnels for passenger and freight trains, and a smaller service tunnel running between them for maintenance access and emergency evacuation. Each one ran 50 kilometers beneath the seabed, connecting Folkestone in Kent to Coquelles near Calais. At their deepest point, they sat 75 meters below the seabed surface. Tunnel boring machines, enormous rotating cutting heads followed by prefabricated concrete lining systems, worked from both ends simultaneously, the British side and the French side boring toward each other. The alignment had to be precise enough that when the 2 sides met in the middle of the channel, the tunnels would connect within acceptable tolerances. The survey work required for that level of accuracy across 50 kilometers under the sea, using 1980s technology, was itself a significant achievement. They met in December 1990. The 2 boring machines, approaching from opposite directions, were off by 358 millimeters horizontally and 58 millimeters vertically across 50 kilometers of tunneling. That is approximately the width of an adult hand. The project employed 13,000 workers across both sides at peak construction. 10 workers died during the build, a number that, like the Empire State Building and the Golden Gate Bridge before it, was lower than the scale of the project might have suggested, but is still 10 people who didn't go home. The cost, however, was a disaster. The original budget estimate was £4.8 billion. Final costs came in at £4.65 billion for construction alone, apparently within range until you account for the financing costs, cost overruns during construction, and the additional capital required when the project ran into difficulties. Total costs reached approximately £10 billion, more than double the original projection. The private consortium that financed the tunnel, Eurotunnel, carried a debt burden that pushed it to the edge of insolvency multiple times in its early years. It underwent a major financial restructuring in 1995, a year after opening. The tunnel opened in May 1994, The first official passenger service ran on November 14th of that year. What had taken 180 years of proposals, false starts, and political obstruction to build was suddenly carrying passengers between London and Paris in around 2.5 hours. The operational history has been eventful in ways that the original projections didn't fully model. A fire broke out in the tunnel in 1996, 2 years after opening. Started by a truck on a freight shuttle. No passengers died, but the damage was significant, and one of the 3 tunnels was closed for months. A second serious fire occurred in 2008. The tunnel's designers had built in the service tunnel specifically for emergencies, and both times it performed as intended. But fire in an enclosed space 75 meters under the seabed is a category of emergency that concentrates the mind. The migration crisis of the mid-2000s brought a different kind of problem. Thousands of migrants attempting to reach Britain gathered near the French entrance to the tunnel and repeatedly attempted to access it on foot, creating security situations that temporarily disrupted services and generated significant political friction between Britain and France. A version of exactly the kind of cross-channel tension the tunnel's 19th century opponents had always feared, though not the kind they had imagined. Eurotunnel, now renamed Getlink, has carried over 500 million passengers since opening. Around 400 trains pass through the tunnel every day. The journey between the 2 portals takes 35 minutes. In 1994, the American Society of Civil Engineers included the Channel Tunnel on its list of 7 wonders of the modern world, recognizing the bored length beneath open water, the precision of the alignment, and the completion of a project that had defeated every previous attempt for the better part of 2 centuries. Channel Tunnel proved to be more complex than anticipated and billions over budget, the same problems that plagued the next megaproject on our list. Ferdinand de Lesseps was the most celebrated engineer in the world. When he arrived in Panama in 1881, he had just completed the Suez Canal, a project widely considered the greatest engineering achievement of the 19th century. More than 1.5 million workers had taken part in building the 193-kilometer-long canal. It took 10 years to build and elevated France's reputation across the globe. Compared to the Suez, the Panama Canal was supposed to be simpler. It was half the size, and the chief engineer had already set a record. While the Suez had been dug through flat desert, Panama was a narrow isthmus. It would take less time, less labor, and could be built at a much lower cost. However, the confidence was misplaced. De Lesseps had decided on a sea-level canal, no locks, just a straight cut through the isthmus at ocean level, the same approach that had worked in Egypt. The problem was that Panama was not Egypt. The terrain between the Atlantic and Pacific coasts was not flat desert, but dense jungle sitting on top of a mountain range. The Culebra Cut, the section through the Continental Divide, required excavating through rock and unstable soil to a depth that made the Suez Canal look like a drainage ditch. Then there was the water. Panama receives around 2.5 meters of rain annually. The Chagres River, running directly across the proposed canal route, flooded with a violence during wet season that repeatedly overwhelmed the excavation sites, washing away equipment and work in hours that had taken weeks to complete. De Lesseps's engineers dug, the jungle and the rain filled it back in, and then people started dying. Yellow fever and malaria moved through the workforce with a speed that no one had fully anticipated. The actual death toll from the French effort remains disputed. Estimates run from 20,000 to as high as 22,000 workers dead over the course of the project, most from disease rather than accidents. The French tried to keep the scale of the mortality quiet. The workers arriving to replace the dead often didn't know what had happened to the men before them. It also proved to be vastly more expensive, and the Lesseps's company went bankrupt trying to raise the required funds. Public confidence had evaporated, and the French effort collapsed in 1889. De Lesseps and his sons were convicted of fraud and corruption. He died in 1894 without ever returning to Panama. Despite wasting close to $100 billion, the excavation sites were abandoned. A decade later, the project had a new bidder. The U.S. President Theodore Roosevelt considered a canal across Panama a strategic necessity and swiftly pushed it through Congress. He secured the assets related to the abandoned canal for $40 million in 1904. The Americans made two decisions that changed everything. The first was to abandon the sea level approach entirely and build a lock canal instead, using the Chagres River rather than fighting it by damming it to create Gatun Lake and floating ships across the elevated interior on a system of locks. The second was to solve the disease problem before doing anything else. Dr. William Gorgas spent 2 years on a systematic mosquito eradication program before major construction began, fumigating buildings, eliminating standing water, screening hospitals, and doing the painstaking epidemiological work that dramatically reduced yellow fever and malaria transmission across the canal zone. It was unglamorous work that saved thousands of lives and made everything that followed possible. Construction proper ran from 1906 to 1914. The Culebra Cut, the same section that had defeated the French, was the central challenge. Workers blasted and excavated through 9 kilometers of rock and unstable soil in conditions that remained brutal even after the disease problem was brought under control. The hillsides on either side of the cut were prone to landslides that could bury weeks of work in minutes. The excavation was restarted repeatedly. At peak construction, 40,000 workers were on site. Around 5,600 died, a fraction of the French toll, but still an enormous human cost. The canal opened on August 15, 1914. A cargo ship called the SS Ancon made the first official transit. Almost nobody noticed. The First World War had broken out 11 days earlier, and the world's attention was elsewhere. What the canal did to global shipping was immediate and permanent. The route from New York to San Francisco, previously requiring a journey around the southern tip of South America, 22,500 kilometers, dropped to 9,500 kilometers. Ships that previously spent weeks at sea saved weeks. Commodities that had been prohibitively expensive to transport became viable. The economics of global trade shifted visibly within years of opening. The canal became the object of political tension almost immediately. Panama spent decades trying to renegotiate the terms under which the United States controlled the canal zone. The process was bitter, protracted, and occasionally violent. In 1977, President Carter signed the treaties that agreed to transfer control to Panama. On December 31, 1999, the United States handed over the canal. Panama has operated it since without incident. The scale of the excavation, the complexity of the lock system, and the fact that the project was completed at all makes it one of the most challenging engineering efforts in history, which is probably why it made its way to the list of 7 wonders of the modern world. An expansion project completed in 2016 added a third set of locks, allowing the canal to handle the massive container ships that the original 1914 design couldn't accommodate. The new locks can pass ships carrying 14,000 containers. Around 14,000 ships transit the canal every year. Each crossing takes between 8 and 10 hours. The canal generates around $2 billion annually for the Panamanian government. De Lesseps' original excavation is still down there somewhere, buried under decades of American and Panamanian expansion, absorbed into the walls of the cut that finally defeated him. The BBC, in 2003, added 2 structures to the civil engineering wonders list that the ASCE had left off. One of them had been holding back the Colorado River since 1935. The other had been connecting Manhattan to Brooklyn since 1883. The argument for including both was difficult to dispute. For 13 years, a man named John Roebling tried to convince the city of New York to let him build a bridge across the East River. The crossing between Manhattan and Brooklyn had relied on ferry services for the entirety of both cities' existence. In winter, when the river froze, the ferries stopped. People were stranded. Commerce halted. The case for a bridge was obvious to everyone who needed to cross the river and had been denied by weather or congestion. The case against it was that nobody believed a bridge of that span was structurally possible. The East River at the proposed crossing is 480 meters wide. In the 1860s, the longest suspension bridge in the world spanned roughly a third of that distance. Roebling was proposing to more than triple the record. He was finally approved in 1869. 2 months later, before construction began, he was standing on a dock surveying the site when a ferry struck the pier he was standing on. His foot was crushed. He refused hospital treatment, insisted on directing his own care using a hydrotherapy method he personally believed in, and died of tetanus 3 weeks later. His son Washington took over. Washington Roebling was 32 years old when he inherited one of the most complex engineering projects ever attempted. He had worked alongside his father long enough to understand the design, but nothing had prepared him for the particular challenge that would define the next decade of his life: the caissons. To anchor the bridge's 2 towers, workers had to excavate down through the riverbed to reach bedrock. The method was pneumatic caissons, massive airtight wooden chambers sunk to the riverbed, pressurized with compressed air to keep the water out, with workers inside digging by hand. As the caisson sank deeper, the air pressure inside had to increase to match the water pressure outside. Nobody fully understood decompression sickness in 1870. Workers who spent hours under high pressure and then returned too quickly to normal atmospheric pressure developed what they called caisson disease, agonizing joint pain, paralysis, and in some cases, death. Over the course of the Brooklyn Bridge's foundation work, roughly 110 workers suffered serious cases. 3 died. Washington Roebling himself went down into the caissons repeatedly to supervise, developed severe caisson disease, and never fully recovered. By 1872, he was bedridden. He would remain largely housebound for the rest of the construction. From his apartment in Brooklyn Heights, Washington Roebling watched the bridge go up through a telescope. His wife Emily, who had no formal engineering training, became the critical link between the bedridden chief engineer and the construction site. She learned enough engineering to carry his instructions to the site supervisors, relay technical problems back to her husband, and communicate decisions with enough authority that the project continued to function. For over a decade, she was, in practical terms, the bridge's operational manager. When the Brooklyn Bridge opened on May 24, 1883, Emily Roebling was the first person to cross it, by carriage, carrying a rooster as a symbol of victory. Washington watched from his window. The bridge had taken 14 years and cost $15.5 million, roughly $500 million in today's terms. 27 workers died during construction. What opened that day was, by a significant margin, the longest suspension bridge in the world, its central span of 486 meters, nearly doubling the previous record. The towers rose 83 meters above the river, making them the tallest structures in the Western Hemisphere at the time. The steel wire cables supporting the deck, each one containing 5,434 individual wires, were a new technology, replacing the iron wire used in previous suspension bridges and allowing a strength-to-weight ratio that made the span possible. 6 days after opening, a rumor spread through a crowd on the bridge that it was about to collapse. The resulting stampede killed 12 people. The bridge was undamaged. P.T. Barnum, apparently recognizing an opportunity to make a point, led 21 elephants across it the following year to demonstrate its stability. The bridge's grip on New York's identity set in quickly and has never loosened. Hart Crane wrote a long poem about it in 1930. The painter Joseph Stella depicted it repeatedly, obsessively, as a kind of industrial cathedral. It has been the backdrop for more photographs of New York than perhaps any other single structure, the towers and cables framing the skyline in a composition that has remained essentially unchanged for 140 years. A German saboteur planted a bomb on it during the First World War. It survived. It survived the construction of the Manhattan Bridge and the Williamsburg Bridge, both of which offered competing crossings and neither of which diminished its stature. It survived the 20th century, the transformation of the waterfront around it, the collapse of the World Trade Center, visible from its walkway on September 11, 2001. It carries around 100,000 vehicles and pedestrians every day. The walkway above the traffic lanes is one of the most walked paths in New York, offering a view of the harbor and skyline that has drawn people since the day it opened. Washington Roebling lived until 1926, long enough to see the bridge outlast every skeptic who had said it couldn't be built. He gave almost no interviews about it. When asked about the bridge late in his life, he was characteristically brief. He had spent 14 years building it and another decade recovering from building it. The BBC in 2003 added 2 structures to the civil engineering wonders list that the ASCE had left off. One of them had been holding back the Colorado River since 1935. The other had been connecting Manhattan to Brooklyn since 1883. The argument for including both was difficult to dispute, starting with the dam. In the early 20th century, the Colorado River was one of the most dangerous rivers in the American West. Not dangerous in the way people romanticize wild rivers, dangerous in a practical, economically devastating sense. Every spring, snowmelt from the Rockies sent the river into violent flood, destroying farms, wiping out irrigation infrastructure, and making any kind of reliable agriculture across the southwestern desert essentially impossible. Then, in the dry months, it would slow to a trickle, leaving the same farmers without water entirely. The river gave nothing on a predictable schedule. It flooded when you didn't need it and disappeared when you did. 7 states depended on the Colorado. All 7 had competing claims on its water. Getting them to agree on anything required the kind of negotiation that takes years and still ends with everyone mildly dissatisfied. The Colorado River Compact of 1922 divided the water between the upper and lower basin states. What it didn't do was solve the flooding, the drought cycles, or the absence of any infrastructure capable of storing water at the scale the region needed. A dam at Boulder Canyon, later moved to Black Canyon, was the proposed solution. In 1928, Congress approved it. Construction began in 1931. The Black Canyon site on the Nevada-Arizona border was, in the summer, one of the most hostile construction environments in the country. Temperatures inside the canyon regularly exceeded 50 degrees Celsius. The canyon walls were sheer and unstable. The Colorado at that location was moving fast, and before any concrete could be poured, the river had to be diverted through 4 tunnels, each one over a kilometer long, bored through the canyon walls on either side. That diversion alone took 8 months. The dam itself was an engineering problem that had no direct precedent. The volume of concrete required was 2.6 million cubic meters, enough to build a 2-lane highway across 5,000 kilometers. Unprecedented for a single structure, that volume of concrete poured as a single mass would generate heat that would have taken over a century to dissipate and cracked the structure in the process. The solution was to pour it in interlocking columns of smaller blocks, with refrigerated pipes running through each one to draw the heat out artificially. The columns were then grouted together once cooled. It worked, but it required a cooling system built into the dam itself. At peak construction, 5,000 men worked the site around the clock in 3 shifts. The canyon offered no natural shade and temperatures that made sustained physical labor genuinely life-threatening. Workers were paid Depression-era wages to do it anyway, because the alternative was no wages at all. According to official figures, 96 workers died during construction, which excludes deaths attributed to heat and carbon monoxide poisoning in the diversion tunnels that the company listed under other causes. The dam was completed 2 years ahead of schedule in 1935. What it created was immediate and transformative. Lake Mead, the reservoir behind the dam, is the largest reservoir in the United States by volume, stretching 177 kilometers behind the dam wall and holding enough water to cover the entire state of Pennsylvania to a depth of around 30 centimeters. The hydroelectric plant embedded in the dam's base generates 4,000 megawatts of power, supplying electricity across Nevada, Arizona, and California. The controlled release of water downstream made large-scale agriculture viable across the desert Southwest in ways that had been impossible before. Las Vegas, 48 kilometers away, exists in its current form largely because of what Hoover Dam made possible. The power, the water, the economic activity generated by construction. The city's modern trajectory begins in the canyon downstream. The dam itself is 221 meters tall and 379 meters wide at the crest. At its base, it is 200 meters thick. It weighs approximately 6.6 million tons. The Colorado River has not flooded uncontrolled downstream since the dam closed its diversion tunnels in 1935. There are 2 bronze sculptures at the dam's entrance, Art Deco figures called the Winged Figures of the Republic, installed at dedication. Between them is a terrazzo floor inlaid with a star map marking the exact astronomical positions of the planets on the day Franklin Roosevelt dedicated the dam, September 30th, 1935. The idea was to give any future civilization that found the site a way to calculate exactly when it was built. The dam draws around 1 million visitors a year. It has appeared in films, been used as a dramatic backdrop, and survived a period in the years after September 2001 when serious security concerns about its vulnerability to attack led to significant changes in public access. A bypass bridge was completed in 2010 specifically to reroute highway traffic away from the dam's crest. The Mike O'Callaghan-Pat Tillman Memorial Bridge now carries vehicles across the canyon 274 meters above the river, with the dam visible downstream. Standing on that bridge and looking back at the dam, what strikes most people isn't the size, though the size is staggering. It's the setting, the sheer canyon walls dropping to the river, the geometric perfection of the concrete curve against the raw rock, the absolute improbability of something that precise existing in a place that hostile. It has been holding back the Colorado River for nearly 90 years without interruption. Since their creation, many of these structures have been surpassed by even bigger construction projects. But these engineering wonders of the world continue to be the reference point for what human ambition can create in a quickly shifting world. Do you think we'll have even bigger dams in the future? And how high can we really build? Let us know in the comments below. If you enjoyed this video, get a taste of some more insane construction behemoths with our video compilation on the biggest mega projects in China. Keep following Signum for more insane stories from the world's biggest mega projects.